Well, thank you so much for coming here tonight to listen to a talk about mathematics. I'm Jim Carlson, president of the Clay Mathematics Institute, which is located on 1 Bow Street, right by the Grafton Pub or Dunkin' Donuts, however you wish to locate it. The Clay Mathematics Institute is dedicated to furthering the creation and dissemination of mathematics. It was formed due to the generosity of Landon and Lavinia Clay. Among our many activities are a series of public lectures. We generally hold 2 each year, 1 at Harvard, 1 at MIT. The spring public lecture will be at MIT, and our speaker will be Ingrid Dobschies, who I think should be viewed as the mother of wavelets, which is a branch of mathematics that has had truly astounding applications. Get the right set of notes here, it helps. So tonight we're having our lecture here at the Mathematics Department, sponsored by the Mathematics Department of Harvard University. We're very, very grateful for their hospitality and for this wonderful venue in the Science Center. Our speaker tonight is Michael Sipser. He is chair of the Mathematics Department of MIT, which has 2 branches, the Applied Mathematics and the Pure Mathematics group. He will speak on the P versus NP problem. I won't say anything about it because Michael can say it much better than I can. Michael was an undergraduate at Cornell University. He received his PhD at Berkeley, and since 1980 he has been at MIT. He's taught many courses there, including everything from basic calculus to graduate courses in the theory of complexity. He's also the author of a widely used textbook, Introduction to the Theory of Complexity. His research interests are largely in the area of complexity theory, but include mathematical logic and combinatorics. So it's a great pleasure to welcome Michael Sipser, who will speak to us about the P versus NP problem. Michael?
Thank you. Thank you, Jim. This thing picking up? Great. So, thank you all for coming. Thanks to the Clay Institute for hosting this wonderful series of public lectures in mathematics. I think it's a great thing. Thanks. I'm grateful. I'm glad to see such a good turnout for a math talk about my favorite topic, the P versus NP question. So let me tell you first. I'm going to jump right in. Tell you a little bit about that. It's a problem in computer science and mathematics. And it concerns the amount of time you need to solve various problems on a computer. Now, even though computers are very fast, for certain kinds of problems, they seem to take a long time. And it's not really well understood why that is. So we're going to explore that. We'll start off with something simple. Let's take the problem 7 times 13. That's an example of something we call multiplication. Just for, in case you're just getting up to speed, the answer is 91. If you look at the reverse problem, given the product, 91, and you want to try to find the 2 numbers that multiply together to give that result, those are called the factors of 91. You could either do that by remembering the previous slide, or you could just start out with the number 91 and figure out what those factors are directly. See, 7 times 13 give you 91. Now, let's look at a slightly bigger example. Now, probably this is one that you're not going to do in your head if you're a normal person. But if you fed it into a computer, you would get the answer out. And what's amazing is that the answer would come out in a split second. But let's take a look at something more interesting. What happens if you look at the reverse problem, the factoring problem, for that particular product? Well, we already know what the answer is, but suppose you didn't write it down from the previous slide. You just went directly from this this product here in blue to the, and you wanted to figure out what the two factors were. Okay. So that's something you could solve on a computer, and actually somebody went ahead and did that. But the difference between this problem and the previous one is that it takes a little longer. In fact, it was 20 computer years of effort required to solve this problem. Now, you may ask, why would somebody care and put all that effort in? Well, for one thing, we're mathematicians, and it's because it's there. Another reason is somebody paid them $20,000 to do that, believe it or not. This is true. And you may think, well, why would somebody pay $20,000 to factor a number? And how can we get a piece of that? So, well, you can. Here's another number. $30,000, in fact. No one knows no one knows the factors of this problem. So if you want to turn on your computers and want to spend, it's going to be more. This is a bigger number. This is a bigger number than the previous one. It's going to be more than 20 computer years, probably a lot more. But you can earn $30,000 that way. Now, why in the world is somebody spending that kind of money to factor numbers? Well, this actually comes from this company called RSA. And you can just Google it if you Google the RSA factoring challenge, you will find this number, the previous number, and a whole list of other numbers, which are $50,000, $100,000, $200,000. This is all true. And the reason why the RSA company is spending that kind of money to factor numbers is not so much because they're interested in that kind of factorization, but they're interested in just getting a handle on the progress that people are making in factoring numbers, because factoring is essential to their business. They're in the business of cryptography, designing secret codes for secure communication between computers. And the kind of code that they use is called the RSA code, is really based on factoring. So if somebody figures a way of factoring quickly, it will break their code. That's something they want to know about, obviously. So that's why RSA is interested in factoring. Now, the question is, why is factoring so hard to solve? Why does factoring take such a long time to solve on a computer? Well, the reason for that is, in contrast with multiplication, where you can kind of zoom right in on the answer, for factoring, all we know how to do is to search for the answer. Given your number that you want to factor, you try dividing by 2, by 3. You can confine yourself just to the prime numbers to save yourself a little bit of time anyway. And you try dividing by 5, 7. If at any point you find one of those numbers that divide evenly into the number you're trying to factor, then you've got a factor. And you can stop there. But otherwise, you just have to keep going on and on and on. The number of possible factors that you might have to search through for factorization problems of the sort I just described is absolutely astronomical. And that's why it takes even super fast computers a very long time to solve that problem. So the process of searching for the answer over a large space of possibilities, kind of one by one in a mindless way, is we call brute force search. And that process is very slow if you have a lot of possibilities that you need to search through. Now, the interesting question here is, do you really need to search? Or is there some way of solving, say, the factoring problem that zooms in on the answer without searching? That would be amazing. And in fact, we don't know the answer to that question. Seems like factoring needs searching, at least as far as we know. I mean, you can do some things that are some improvements on the simple-minded method that I gave you and cut down the search space somewhat. But the only procedures that we know still involve searching through a lot of possibilities. And we don't know if you can eliminate that or not. But let's turn to another example. Here's an example I call the clique problem. So you're given a network here of nodes, and nodes are little circles and lines, which might represent something else. Say, for example, the nodes might represent the members of the math department at MIT. Okay? And we'll draw a line. I'll leave off the names. We'll draw a line connecting two nodes if those two faculty members are friends. Okay, so you can see we have a pretty friendly department, more or less. And what I'm interested in doing, sometimes I host parties now and then, and you'd like to invite people over to your home who are all mutual friends of one another. Okay, so a group of people who are all connected, or a group of nodes who are all connected by lines with one another, is called a clique. So over here we have a 3-clique. This is a 4-clique, 4 nodes all connected by lines, and so on. And if what I'm interested in doing is finding among the faculty, among these nodes, groups which form cliques, presumably as large as I can get, so I can have a decent-sized party. So over here I got a 3-clique. Down here I got a 4-clique. Question is that the best I can do, or maybe can I find a bigger clique than that? Well, if you're really quick, you can see that, in fact, there is a 5-clique in this graph. Here it is maybe a little more clearly. But the point is that if you want to try to find a clique, say in a bigger graph, here's a graph with even more. Here's a network or graph with even more nodes. The number of possibilities, say, if you want to look for a clique, say, of 8 nodes in here. That's not a clique, but if you sort of want to try to find one, perhaps, with 8 nodes in it, you just have to, as far as we know, you have to search through all possible subsets of 8 nodes to see if any one of them turns out to be a clique. And the number of possibilities that you would have to go through to do that is large. And in fact, if you had, instead of just 100 nodes, as I've described here, if you had hundreds of nodes, which is still a pretty modest-sized problem, and you tried to find the biggest clique possible, or some target-sized clique of a reasonably decent size, it would take centuries, maybe even millennia, of computer time to search through all the possibilities. You see, it's a very similar kind of situation with factoring, and it's even more similar in that you can ask the same question. Do you really need to search? Or is there some way to zoom in on that big clique quickly without searching? We don't know. So both the clique and the factoring problem are examples of what I would call needle in the haystack problems. In case you're not familiar with haystack, here's an example. Big pile of hay, and somewhere in there is a needle. To search for that needle, as you can imagine, is going to take a long time. Here's a cartoon sort of giving the idea. Somebody actually found the needle after searching. So it's amazing what you can find on the internet these days. In the case of this sort of example of looking for a needle in a haystack, here's on my model of a haystack. If you want to, you can ask the problem, is searching necessary to find the needle? Well, perhaps you have a magnet. Then, bingo, you get the needle right away. You don't have to search at all. So the question that we're asking in the case of factoring and clique, is there some kind of mathematical analog to the magnet that pulls out the answer without having to search for it? In neither of those cases do we know. And in fact, that phenomenon is very, very pervasive. It's very widespread throughout problems in engineering, in economics, in optimization, in science. For example, if you looking at problems involving scheduling classes or exams where you're trying to minimize the number of conflicts, the only way to do that, which finds the best possible answer, involves searching through large numbers of schedules. Or if you want to color a map with the smallest number of colors so that no two adjacent countries end up with the same color, you might have to search through a lot of possible colorings in order to find the one that's the best possible. Or if there's a problem in computational biology where you're given a protein sequence and you're trying to find the configuration that that sequence will fold up into to give you a sense of the function of that protein inside the cell. It would be great if we could solve that on a computer, but the only way that we know how to do it would involve trying to search through all possible configurations of the protein. It takes too long. This is a real practical problem that people would love to be able to solve. It's just beyond our computational ability to solve it by searching, and no one knows if there's a faster way. Another problem of interest to mathematicians is the problem of theorem proving. Another searching type problem. If I want to know, is there a proof of a theorem of a certain length? So, okay, I'm given some mathematical statement, say, and I want to know, is there a proof which is at most 100 pages? Well, I could do that in principle by a computer. I can make that check by computer by searching through every possible proof of 100 pages long and seeing if any one of them actually works. But of course, that's going to take a horrendous amount of time. Is there some way to find that proof more directly? No one knows. It would seem incredible if there was, but we don't know. We don't have a proof that you can. And it goes on and on. There are many other problems of this kind where searching seems to be necessary, but we don't have a proof that it really is. So that's the P versus NP question. Sort of informally speaking, can we solve searching problems without searching? Okay, I'll say more about that in a second. But let me first help you to see or explain where the terminology P versus NP comes from. It comes from these two classes of problems called P and NP. P stands for the problems that you can solve quickly, the so-called polynomial time problems. And I don't want to get too technical about it, but for our point of view, polynomial time, where you're considering how long the procedure is going to run in terms of the length of the input to the procedure, and it only grows by a polynomial number of steps, compared with an exponential number of steps, which is what you would need if you had a searching problem. Polynomial time is considered fast. So the P problems are the ones we consider to be quickly solvable. Those are the ones that don't need searching. In contrast with the NP problems, those are the problems which, in addition to that, are problems that might involve searching. Okay, so the P problems are the problems that you can solve quickly. The NP problems are the problems that might involve searching as well. But it's searching of a particular kind. And this is a little bit of a tricky point, that these are problems where you can solve them by searching, but once you've found the answer, you can check that it's right quickly. So finding it might be hard, but checking it is easy. So what I mean by that is, think of the examples of factoring and clique. Those are both NP problems. So in the case of factoring, it might be hard to find the factors. But once I found them, I can check that they work just by multiplying them together and seeing if I get the right result. So checking is easy. That's the essence of NP. Same with clique. If I'm trying to determine, does my net, is there a net within my network, are there 100 nodes that form a clique that are all connected to one another? It might take me a long time to find it, but once I have found it, I can check that it works, that it's really 100 nodes, that they really are connected with one another, and so on. That check I can do easily. That's the essence of NP, which stands for non-deterministic polynomial time. That you may not be able to find the answer quickly, but you can check it quickly. So in terms of visually speaking, both of these classes are classes of computational problems. The NP problems are the ones where you can check them easily. The P problems are the ones where you can solve easily. And the mathematical question is, are those two classes the same? Is checking easily checkable problems the same thing as easily solvable problems? Because the easily checkable problems are the ones that you can solve with searching. So if the two classes, P and NP, are the same, that says that any problem that you can solve with searching, you can also solve without searching. So searching can always be eliminated if P equals NP. However, if we show that P is different from NP, then we know that there are certain checkable problems which are not, certain easily checkable problems which are not easily solvable. And so that tells us that there are certain problems that really require searching, can't be eliminated. See, if you didn't follow that exactly all, the thing to remember is that either P equals NP, which means you can always eliminate searching, or P is different from NP, which tells you that sometimes searching is necessary and can't be eliminated. Okay? Which is the latter is what we expect to be true, but we don't know how to show it. Okay? So this either-or situation is unresolved at this time. Okay? Let me tell you a little bit about the history of the problem. In the literature, anyway, the subject goes back to the mid-1960s when various, mostly mathematicians, started looking at the emerging computer technology and started building a mathematical theory around it. And they did things like defining what it means for various, coming up with formal models of computers and measuring the amount of time that those models of computers need to solve various kinds of problems. So they basically set up the mathematical framework of the theory and proved a bunch of interesting theorems at the same time. Now, some years after that, in the early 1970s, there were several papers by Cook, Levin, and Karp which established the P versus NP question as an important one, and this companion notion of NP completeness, which I'll talk about in a bit. So it really, in the literature, the P versus NP question traces its roots back to the early 1970s. Okay. But about 15 years ago, an amazing discovery was made. It turns out that in the correspondence between two mathematicians, the whole idea of P versus NP had been explored back in 1956. And that was this letter that Gödel wrote to von Neumann, which was discovered in von Neumann's archives. So here is a copy of the letter. I'll actually explore some details of the letter in a minute. For one thing, it's in German, so that's a little bit of a disadvantage. And it's also a little hard to read from back there. But we'll look at it in a bit more detail. But just in case you don't know who Gödel and von Neumann were, Gödel is considered to be the greatest logician of the 20th century. In the 1930s, he had a whole series of absolutely remarkable mathematical breakthroughs, one of which is the incompleteness theorem, which tells you that in any reasonable mathematical system, there are certain true statements which cannot be proven to be true within the system. And that sort of devastated certain mathematicians of that day because they had believed that any mathematical question would ultimately be resolved if you just worked hard enough. Gödel showed that that wasn't true. There are some things that in some sense might never be known. And this happens to be the 100th anniversary of his birth at the same time as being the 50th anniversary of that letter. So it's a nice time to talk about it. John von Neumann was a great, tremendously versatile mathematician who worked in a whole bunch of different fields in pure and applied mathematics, and as well as in physics and in other fields. He was at the Manhattan Project, and he was also a very early computer scientist, and is known, for example, for this von Neumann architecture. That's sort of the way pretty much all computers are set up today. So the idea of a stored program computer. So let's look back again at his letter, and I hope this comes through. We'll see. I sort of focus in on a few sort of key pieces of the letter. Translated for your benefit and mine. So it starts off, Lieber Herr von Neumann. This is the salutation, dear Mr. von Neumann. And here's the date, March 20th, 1956, in Princeton. Now, and one thing that's sort of curious is both Gödel and von Neumann were at the Institute for Advanced Study at Princeton, presumably with offices down the hall from one another. So it's sort of strange that Gödel is writing von Neumann a letter like this. However, one does have to point out that von Neumann was very sick at the time, and in fact was dying and died within a year. So perhaps he wasn't, around. Maybe he was at home or maybe in the hospital. I don't know. So that may have been why he wrote him a letter. In fact, the beginning part of the letter, the first page of the letter, refers to von Neumann's illness and Gödel's hopes that he recovers and so on. But then he turns to a mathematical question, and this is the mathematical question he talks about to von Neumann. He says, suppose we have a machine. He doesn't use the word computer, he says a machine. And machine can, he actually uses the word, it's amazingly modern language in this whole letter. You have to read the whole thing to appreciate it. But it's very phrased in a very modern terminology, which didn't exist back then. I mean, he was just making this all up for the first time, really. But he says, suppose you have a machine which can tell whether a mathematical statement has a proof of length n for some specified n. How much time does that machine need? And remember, that's the question we talked about just a few slides back. This is a classic searching type problem. The machine can certainly get the answer, but it would have to search through all possible proofs of length n, and that would take a long time. So here is what Gödel says. Die Frage ist, blah, blah, blah. The question is, translated, how fast does phi of n grow for an optimal machine? And you can sort of see it and think if you can read the handwriting there. Phi of n is the amount of time the machine needs to make this test of whether the mathematical statement has a proof of length n. So in other words, if phi of n is polynomial, then this problem becomes in P. If phi of n is more than polynomial, then it's not in P. So in fact, really what this thing is saying, this little section here is the P versus NP question right there. Kind of amazing that in a very real sense, the P versus NP question has been explicitly stated in this letter. Then he goes on to talk about that this would be very important to resolve this question. It's a very significant one way or the other. And over here, oops, he refers to Blossen probieren, which I think loosely translates to brute force or exhaustive search. I think it literally means something like blind or bare trying. But he's aware of this issue of exhaustive search as what would happen is if you couldn't do anything to test if this proof of length n existed. And then he goes on to mention the problem of testing primality. And in fact, how many steps you need to solve, in general, finite combinatorial problems. Such as, like, he doesn't say this, but finite combinatorial problems would be like the clique problem or scheduling problem or stuff like that. So he really has a vision of what's important about this question and really kind of predicted where the field is going, where the field went over the next 15, 20 years. It's just, I think, an amazing document in the history of science that this thing was discovered. Anyway, so in the 50 years since Gödel's letter, the P versus NP question has kind of attained a certain almost mythic status within computer science field, within theoretical computer science. It's kind of now thought of as the holy grail problem of theoretical computer science. And also within the mathematical community, it's considered to be one of the great problems in contemporary mathematics. The Clay Institute has been responsible for this list of kind of great math problems. I guess they organized a committee of folks, and I'm not sure I know the whole full background, but there was a group of mathematicians who put this list together in the year 2000, sort of patterned after the list that Hilbert put together a century before. And these are great unsolved problems of mathematics today, which kind of are challenge problems for mathematicians for the coming century. And as you can see, P versus NP, the P versus NP problem is one of the problems on this list. I was happy to see that. One thing that's different between the Clay list and the Hilbert list is that the Clay Institute is also offering $1 million for the solution to any one of these problems. So that's a pretty nice thing. And you might notice that the top problem on the list has a little check mark there. It doesn't have a bullet anymore, because that problem has actually been solved. You probably know the story of Perlman. I'm not going to get into that whole complicated mess. But he didn't accept the Fields Medal a few months ago or so. And even though he's the one who solved this problem, and it's not known yet whether he's going to accept $1 million. That has not been, there's a sort of a 2-year delay before they give the $1 million out. I guess it's a little bit more than just, got to be careful with those $1 million. So anyway, so that's, actually, I had to guess. I bet he'll accept this one. But I really, maybe not. Who's to say? So yeah. Oh yeah. So before I get to that, I want to say one thing about P versus NP. Getting back to that question. In some sense, P versus NP question says, do you really need to search when you have a searching problem? And in some sense, if you might think that's kind of obvious. Obviously, you need to search if you have a searching problem. And believe it or not, I get a couple of times a year, I get a manuscript of someone purporting to solve the P versus NP question. For some reason, I get sent these things. I don't know why. And they invariably, even though they're like 40 pages long, all the essence of it is, the problem's obviously true. That's the content pretty much always in these papers. And there's a lot of complicated calculation, but they basically all say, well, you have to solve these problems by searching, and searching takes a long time. Calculate, calculate, calculate. What I want to show you is that sometimes you can avoid searching where you might think you would otherwise need it. And I'm not going to be able to do that in detail because it would get too technical, but I want to give you a little bit of a flavor of how that might happen. And that's the case of testing whether a number is prime. Okay? So this is actually one of the problems that, the problem that Gödel mentioned in his letter as one that might seem to require searching. And superficially, the way you would test if a number is prime is the same way you would factor a number. You would do trial division of lots of possibilities. And if you fail to find a factor, then you know the number is prime. If you find a factor, you know it's not prime. But that's very slow, as I pointed out, that searching type method. But we now know that there are dramatically faster ways of testing if a number is prime. And I'll give you a little flavor of how that goes. And these all sort of rest on a centuries-old theorem due to Fermat in number theory. And this is as technical as the talk is going to get. So I would say this is a technical. I keep on pointing at my my laptop there, which I know you can't see. This is a okay, let me walk you through this. I mean, it's worth trying to understand this because it's very nice. So try to bear with me. What this theorem says is that if you have a prime number, p, like take 7, for example, and you have a natural number a less than p, like take 2, for example, so p equal to 7, a equal to 2, then if you raise a to the p minus 1 power, you always get 1 modulo p. And saying that in English, it says that if you take the number a, which is 2 in our example, you raise it to the p minus 1 power, then you divide by p and take the remainder. So throw away the quotient, but only look at the remainder after you do the division. You always get 1 for the remainder. So let's actually walk ourselves through an example. So if p is 7 and a is 2, as I mentioned, you raise 2, which is a, to the 7 minus 1, or 6 power, which is 64. Now you divide by 7 and take the remainder. Now 63 is a multiple of 7. So 64 has a remainder 1 when you divide by 7, and it works. Okay? And it works whenever you meet the conditions of the theorem. For any prime in any a and any such a, you're always going to get 1, which is actually kind of, so you might think big deal, but it's kind of amazing that this works if you actually try it out on a bunch of examples. And just in contrast, if you try an example where p is not prime, you'll see it fails to work. So if you take p equal to 15 and a equal to 2, then you raise 2 to the 14th power. You get 16,384, and you divide by 15, and take the remainder, you get 4, which is not 1. So you see that equation fails in the case where it can fail anyway, in the case where p is not prime. And what's amazing about this is that that calculation that I just did proves to you that 15 isn't prime. Now, of course, we knew that already. But this proves it to you in a different way. It doesn't prove it to you by exhibiting the factors 3 times 5 of p. It proves it to you by saying, well, p fails to have a property that we know prime numbers have, and therefore it can't be prime. And the thing is that you can use this as a basis of a test, basis of an algorithm, which can test primality without going through the factorization process. And in fact, initially it was a randomized algorithm, and since, it's been since sort of, with lots of additional ideas, been made into a deterministic algorithm. And now we know that the problem of testing if a number is prime can be solved quickly in polynomial time. Okay, so searching can be eliminated. Okay, now let me tell you a little bit about this notion of NP completeness. All right. I would say NP completeness was perhaps the first and maybe the only important step that's been made towards solving the P and NP question. And it's a nice kind of explainable idea. It's kind of amazing in its own right. What NP completeness is this. It tells you that the problems in NP, these searching problems, are in many cases linked to one another. And what I mean by that is if you find a way of solving the clique problem, remember this, this problem with the network of nodes, if you can find a way of solving that problem without searching, you immediately get a way of solving the factoring problem without searching, even though those two problems don't look anything like one another whatsoever. A fast way of solving clique will immediately translate into a fast way of solving factoring. Why would that be true? Well, the reason for that is that there are these transformers that can convert factoring problems into clique problems. So if you have a fast way of solving the clique problem, and you want to solve your factoring problem, you just push it through the transformer. Transformer thinks for a while, and spits out a clique problem. I can do that again if you want. And the nice thing about the clique problem that gets spit out is that if you find a large clique in that network that gets produced, it immediately translates into the factors of the original factoring problem. So you get the idea. That's why the clique problem is related to the factoring problem in this way. And incidentally, the reverse transformation is not known to be true. So we don't know how to convert clique problems into factoring problems, only this way. However, clique is still, this phenomenon is not unique to factoring in that you can convert any NP problem to a clique problem. So what that tells you is that the clique problem is, in some sense, the granddaddy of all problems in NP, because you can convert any NP problem into a clique problem. And therefore, if you can solve the clique problem quickly, you can solve any NP problem quickly, and then P equals NP. That's what it means for clique to be NP. It's not the only one. There are many other problems which are NP complete, but clique is one of the problems we were looking at. Okay. Oh, yeah. So let me also mention a little bit more about NP, just to sort of clarify what's going on with NP a bit. I said that NP are the problems where you can solve by searching, but where you can also check the answer quickly. So just to contrast that, there are certain problems that you can solve by not be able to check the answer quickly. It's not a given that just because you can solve it by searching that you can always check the answer quickly. So take the case of chess. And you want to know which side would win under optimal play. If both sides played perfectly, would white win, would black win, or would it be a draw? Nobody knows the answer to that problem. In principle, you could figure it out by going through the entire game tree of all the possible games that you could have in chess, but that's an astronomically big number, and it would take a horrendous amount of time, longer than the lifetime of the universe. And so it's not practical to do that. But moreover, suppose you did it, and you determined white has a forced win if both sides play optimally. Now you want to convince me of that. Now you want to check that that's the right answer. There's no simple way to check it. The only way to check it is to essentially walk through the whole thing, do the whole thing over again. Okay, so that's in contrast if I'm trying to get the sense that this is a searching, seeing which side has the win under optimal play is a searching problem, but it's not an NP-type searching problem. It's kind of in some worse than NP, because you don't even have this feature that you can check the answer quickly. Okay? So just sort of summarizing some of the information that we've been discussing recently, we have the classes P and NP, and the four problems that we've discussed, multiplication, factoring, clique, and optimal game strategies, are kind of appropriately placed. The games is outside of NP, clique and factoring are in NP, but not known to be NP. And actually, in all of these cases, this is just conjectured, the conjectured picture. Things may collapse down. And multiplication is known to be NP. Now, complexity theorists have been working on the P versus NP question, for 30 years or so, but they've been doing lots of other stuff too, not just beating our heads against the wall on just that one problem the whole time. And one of the things that was done is to devise even more complexity classes, and in fact, a rich system of classes that capture all sorts of features of complexity of different problems. So there's actually a rather rich kind of, I don't know what to call it, classification system for computational problems according to all sorts of different parameters, the amount of time you need, the amount of space you need, whether you can solve it more quickly with parallelism or randomness, and so on. And it's been populated by different problems that these are real problems that people are interested in solving, that occur, as far as we know, at different positions within this hierarchy. Now, and I also want to mention that this hierarchy is by no means a static object. The things are changing. Certainly, if p was proved equal to np, that would affect this radically. But there are changes that are occurring every few years as new discoveries are being made. So, for example, if we focus our attention on the primality problem, as I just mentioned, it's now known to be in p. But if we just turn back the clock a few years, we would only know that primality would be solvable in what's called randomized polynomial time. And it was this result that came out in 2002 that moved primality down one step lower in the hierarchy. OK, so got this p versus np problem. What can we do about it? For one thing, I write on the slide, how do we prove p different from np? That partly reflects my bias. I don't believe p equals np. I don't believe that we can solve search problems without searching. I believe that, as most, I'm not unique, most of the other people in the field feel the same way, that many of these problems really do require searching. We just don't know how to prove that. And then why is it so hard to prove? Well, the reason is that computers or computer algorithms can operate in very clever, unforeseen ways, just like in the case for primality testing. There's all sorts of devilish, fiendish, bizarre ways of solving problems that we might not have thought of. And it's very difficult to prove that none of those can possibly work. In a sense, by proving that none of those can work, the computer kind of becomes your adversary. You want to show that this potentially fiendishly clever machine, no matter what complicated thing it gets programmed to do, it's not going to be able to successfully solve one of these searching problems. It's such a rich class of possibilities, very hard to get your hands on that and show that none of those can work. So what do we do? So here's a strategy that myself and some other people have taken on over the years, is try to limit the power of the machine by kind of handicapping it in some way. OK? And then for this handicap machine, it can't run anymore. It can only limp. And when you have a machine that can only limp, maybe you have an advantage in being able to prove it's going to have, you're limiting the kinds of operations it can do. You're limiting its behavior in a certain way. And maybe for these limited machines, you have a better chance of proving that they really do need to search. There are fewer clever things they can do. If you are unsuccessful, limit it even further, until you've got the thing so limited that you can finally say something. And hopefully, you get some insight by doing that. And then maybe you can start eliminating these limitations, and you work your way up, because it's hard to tackle a very hard problem from nothing. You would like to break it down into a series of steps if you can, and you kind of eliminate these handicaps one by one, and hopefully you can build back up to getting an idea of how to tackle a general machine, which is unlimited. That's the hope anyway. OK. Here's another approach. Well, in combination with that, here's an approach that people take, is they try to figure out a way of finding an input to the machine on which the machine would fail. So here's a machine that operates quickly. It doesn't search. So presumably, this machine is not able to solve, say, the clique problem. But how do you prove that it can't solve the clique problem, if it's not able to search? Well, you want to find some kind of an input, an example of a clique problem, which is particularly difficult. And you're more likely to find difficult problems among large problems. So saying it somewhat mathematically, if you're trying to exhibit the difference between polynomial time and exponential time behavior, you're better off looking at large n, because then the difference becomes even more clear. And kind of carrying that to the extreme, it might make mathematical sense to try to run the computer on infinite inputs, if you could make sense of that. And I think in some ways you can. And maybe by running the thing on infinite inputs, you can get some insight into what makes the problems hard and learn something back about the finite case. You know, again, none of these things have paid off. Otherwise, I would be giving a different talk today. But those are ideas that people have tried. OK, so drawing to the end of my talk, will the P versus NP question ever be solved? Well, it seems clear that the collection of techniques that we have at present is inadequate. We're going to have to develop new methods in order to be able to tackle the P versus NP question. Let me just tell you, I mean, I'm personally an optimist that it will be solved one day. Let me tell you a little story about that. When I was a graduate student back in the mid-'70s, I made a bet with one of my fellow graduate students. Happens to be Len Adelman, who was the A from the RSA code. This is before RSA code was developed, which stands for Rivest, Shamir, and Adelman, to give everybody credit, by the way, if they're here. So Len, I made a bet with Len Adelman. We were both thinking about the P versus NP question. This is 30 years ago. And I made the bold claim that the P versus NP question would be solved by the year 2000. And I bet Len an ounce of gold, which was a lot of money for a graduate student. Well, I paid off. Luckily, the price of gold when I was a graduate student was around $700 an ounce. Now it's around $600 an ounce. When I paid off, it was around $250 an ounce. So I got lucky there. But that's anyway. That's my story. And I don't know. I think I'm still hopeful that we'll see the solution. It's a great problem, and I'm looking forward to seeing what happens with it. So that's the end of my talk. Thank you.
Thank Michael for a really fine talk, and I think we can take a few questions.
Yes.
What if I change the problem a little bit and say, I don't really need to solve an algorithm that will solve all of the particular class of problems in polynomial time, but I settle for solving most of them, say 90%, or I settle for an algorithm that's guaranteed to produce a solution that's not necessarily optimal, but that's within some factors of optimal.
Yeah. Sure. I mean, there's, if you're willing to settle for less than the best in many different senses, then you can solve these problems, in some cases, quickly. So if you're willing to settle for an approximate solution instead of finding the biggest clique, well, clique is probably not the best example, but I mean, there are other, because in some cases, it's known that even getting an approximate answer is as hard as getting the best answer. But scheduling might be a better example. I'm not an expert in approximation algorithms, but there are cases where if you're willing to settle for an approximation to the best solution, then you can do it quickly. But yeah, so maybe I should just leave it at that. Is that good enough for you? Yeah. Yes.
And you shall fill it with numbers for every row, every column, and every line as exactly one series numbers from 1 to 9. Is that NP complete?
That's a Sudoku, whatever it's called. Yes. Is that NP complete? Yes. Yes. Thank you. Actually, I don't know, but it's claimed that the answer is yes.
Yes, in the back there. No, you.
What if every node in the network in the clique problem is a computer? Is there a distributed algorithm that can solve the clique problem quickly over that batch of computers?
Well, is there a distributed computer that can solve it? Well, I mean, if there is a distributed computer with a moderate amount of processors, you could simulate that with an ordinary sequential, single processor computer, just by, that one machine just taking, pretending to be each one of those distributed machines one at a time. So it's not going to change things tremendously unless you have an enormous number of distributed machines available to you, like an exponential number of distributed machines.
Right.
So
in that case, is the problem simplified?
yeah, then in that case the problem would be simplified. But in a sense, that is an impractical number of machines to throw at the problem. You were talking about, instead of working for 20 computer years of effort, you might have to have, quadrillions of computers or more than that, working in parallel. So it doesn't really buy you anything that's going to change the picture dramatically.
Yes.
I was a little confused by the statement of the clique problem.
Yes.
It seems like you gave two different ones. One is, can you find a clique of a certain fixed size?
Yes.
The other is, can you find the largest clique?
Right.
Clearly, the fixed size one you can verify is
Right.
verify, but the largest one.
Yeah, I was trying to be careful when I made my actual statements about NP. So the question is, there were two slightly variations of one another in terms of the clique problem. Am I just looking for the largest possible clique in the network, or am I looking for a clique of a certain specified target size? The latter is the one that's in NP. The other one is not an NP problem because you can't check that you actually found the biggest one. That's not an NP type check to make. But if you can solve one of them without searching, you can solve the other one without searching. They're both very closely related computational problems. And so I was sort of using them interchangeably depending upon what sort of worked best in the sentence.
One last question. Yes.
I believe you mentioned Gödel's theory.
Yeah.
And what makes you think that P depends on NP is movable?
That's a great question. I like that. What makes me think, because Gödel had mentioned that there are certain questions which are, perhaps unsolvable in mathematical systems. Maybe P versus NP is one of them. And certainly there are people in the community who subscribe to that possibility and who think, in fact, P versus NP may be just one of those questions that can't be resolved. There's no, at least in terms of proving it one way or the other. And I can argue that both ways. My personal view is that it's a very concrete, down-to-earth kind of a question. It's not the type of question that you would normally think of as being one which is independent of axioms, like the axiom of choice or the continuum hypothesis, which concerns infinities and things that are very far away from ordinary intuition. It's a very kind of concrete question, P versus NP. And for that reason, I think it's, that I don't know if there's anything to back this up, but I think that kind of a question is more likely to be one that's going to get resolvable within our axiomatic system. On the other hand, there is something kind of somewhat close to the foundations of mathematics in the P versus NP question. Just by virtue of thinking that Gödel himself, who was a logician, was thinking about it. When you're thinking about algorithms It's closely related to the notion of proof. And then you're talking about logic. And it is true that questions in logic are more likely to run into this danger of unprovability. And so that gives a little bit of credence to that possibility. But my personal view, and it's just an opinion, because nobody knows, that it is solvable and that will be solved someday, though I'm not taking any more bets.
Well, thank you very much for coming.
Thank you.